So I want to begin by getting everyone on the same page about what we're talking about. There's a lot of use of the word AI bandied about in the media, in corporate pitch decks. Pretty much everyone is doing AI if you believe what the pitch decks say. So of course it has meant from the beginning, even going back to the 1840s, when Charles Babbage and Ada Lovelace were talking about it, making their machines intelligent. But if you're actually going to do it, you have to take the next step. Okay, well, what does that mean? And sometime in the 1940s, this idea gelled, which was really borrowed from economics and philosophy, that machines are intelligent to the extent that their actions can be expected to achieve their objectives. And this is so prevalent that I've called it the standard model. It's also the standard model of control theory, of operations research, to some extent of economics, where we define objectives, we create optimizing machinery for those objectives, and then we set off the machinery and off they go. So I'll be arguing later, actually, that model is incorrect, and it's actually the source of a lot of our problems. But the goal of the field since the beginning, and you can find this very explicitly in the writings and speeches of some of the founders of the field, is to create general-purpose AI, not specific tools like equation solvers or chess programs, but general-purpose AI, meaning that it can quickly learn to behave well in any task environment where the human intellect is relevant. We don't have a formal definition of generality, but I think we will know it when we see it, and maybe Ken already saw it. So let me begin by saying that there's a reason we're doing this, right? Not just because it's cool or fun or profoundly interesting, but it could be extraordinarily beneficial for our civilization, because our civilization is made out of intelligence. That's the material from which we build it. And if we have access to a lot more, then we might be able to have a much better civilization. So by definition, from what I said about general-purpose AI, if we had access to it, we could use it to deliver at least what we already know how to deliver with the intelligence that we have, which is a good standard of living for hundreds of millions of people, but we haven't yet extended that to everybody on Earth. But general-purpose AI can do it at much greater scale, at much less cost. So we could, I think, deliver a respectable standard of living to everyone on Earth. And if you calculate the net present value of that, so that would be about a tenfold increase in GDP, which tells you how far we have to go. It will be about $13.5 quadrillion of net present value. So that gives you a lower bound on sort of what is the cash value of creating general-purpose AI, right? It gives you a sense of what's going on right now, right? The various entities that are competing, whether you think of China and the US or Microsoft and Google, that's the size of the prize. So it makes all the investments, all the numbers that we've ever talked about are just minuscule in comparison. And it also creates a certain amount of momentum, which makes ideas of, okay, well, we could just stop doing this, probably difficult to implement. But of course, we could have more than that, right? We could have much better healthcare. We could solve a lot of scientific problems that are too hard for us right now. We could deliver amazingly good individualized tutoring-based education to every child on Earth. So we could really perhaps have a better civilization. Actually, I just gave a talk at the OECD where I had politics at the end of that, and people laughed. So I took it off again. And towards this goal, we are making a lot of progress. I mean, the self-driving car, is now commonplace on the streets of San Francisco. And I remember John McCarthy, one of the founders of the field, saying that he would be happy when a car could take him to San Francisco Airport by itself. And that's now something that is perfectly feasible. This is some work from my group. One of my PhD students, Nima Arora, developed the monitoring system for the Nuclear Test Ban Treaty. This is developed not using deep learning, but actually this is a large-scale Bayesian inference engine and is running 24/7 at the United Nations in Vienna. This shows the accurate detection of a nuclear explosion in North Korea a few years ago. So there's the entrance to the tunnel down there that was later found in satellite images. This is our estimate in real time of where the event happened, about 300 meters from the tunnel. And then we have the amazing things that generative AI does. So here's one of my favorite examples. Using DALL-E, you ask it for teddy bears mixing sparkling chemicals as mad scientists in a steampunk style. And this is what it produces in a few seconds. Right? So this is pretty amazing, right? Particularly given that for us to do this, right, we would need a rendering engine, which is hundreds of thousands of lines of graphics code. It doesn't have a rendering engine. It doesn't have any graphics code. And yet it's able to produce this image. It's not perfect. The teddy bear seems to have a foot where he should have a hand, and so on, but it's pretty amazing. And then, of course, we had what was China's Sputnik moment, as it's often described, the defeat of human world champions at Go, which was predicted after the defeat of Garry Kasparov to take another 100 years, because Go was thought to be so much more complex than chess. I'll tell you a little bit more about this later. Okay, so how are we doing this, right? How are we filling in this question mark between the sensory input of an AI system and the behavior that it generates? And there have been various approaches over time. The one that's popular right now is this, right? You simply fill that box with an enormous circuit. That circuit has billions or trillions now of tunable parameters, and you optimize those parameters using stochastic gradient descent in order to improve the performance on the objective that you've specified. A much older approach was popular in the 1950s, where instead of circuit in the box, you had Fortran programs. And rather than just stochastic gradient descent, you also did crossover. In other words, you took pieces of those different Fortran programs and mixed and matched in a way that is reminiscent of evolution. So that didn't work in 1958, but you should keep in mind that they were working with computers that were at least a quadrillion times slower than the ones we have now. So we are using, in a typical machine learning run now, a quadrillion times more computation than they typically used then if they did even a multi-day machine learning run. Okay. For most of the history of the field, we pursued what we might think of as a knowledge-based approach, the idea that intelligent systems have to know things, right? That seems so fundamental and so obvious. And we built technologies around that principle. Initially, technologies based on logic, where the knowledge was represented as formal sentences in a mathematical logic. Later on, we embraced uncertainty, developed technologies based on probability theory with the advent of Bayesian networks. And then in the 2000s, in some sense, produced a unification of those two approaches with probabilistic logics or probabilistic programs. And I'll talk some more about that later on. And the advantage of building knowledge-based systems is that each element of a knowledge-based system has its own meaning and can be verified and checked against reality separately. And that provides an enormous combinatorial advantage in the rate of learning and the ability of a system to fix itself when something isn't working. So let me give you an example of what I mean by a knowledge-based approach. Right, so here are a pair of black holes about 1.2 billion light years away. So a good distance across the known universe, not all the way across, but a good distance across. And about 1.2 billion years ago, they started rotating around each other. And as they did that, they lost energy and became closer and closer. And they started radiating gravitational waves. At the peak level of radiation, they were emitting more energy, 50 times more energy, than all of the stars in the universe. So a quite cataclysmic event. 1.2 billion years later, just by coincidence, we had completed the LIGO, the Large Interferometric Gravitational Observatory, which is designed to detect exactly this type of event. The gravitational waves emitted by this, the type of collision of black holes. So this is several kilometers in length. It contains enormous amounts of advanced technology, lasers, lots of computers, incredible materials, and it measures the distortion of space caused by these gravitational waves. And how big is that distortion of space? Well, on relative to this scale, it's the distance to Alpha Centauri relative to the width of a human hair. So if you change the distance to Alpha Centauri, which is 4.5 light years, by the width of a human hair, this system would be able to detect that change. So that's how sensitive it is. And they predicted what that distortion would look like if there was a black hole collision like this. And it looked exactly the way they predicted. They could even measure the masses of the two black holes and so on. So this was the result of knowledge that we as the human race accumulated, the knowledge of physics, of materials, et cetera, et cetera, et cetera, over centuries. And so if we're going to create general purpose AI, it needs to be able to do at least this, right? Because humans did this. It's hard to see how we would train a deep learning system. Where would we get all the billions of examples of different gravitational wave detectors to train it in order to figure this idea out, right? It starts to just not even make sense when you think about things, when you don't think about things in terms of systems that know things.